And once again, my name is Woojin Park, and I'm with the Department of Industrial Engineering at Seoul National University. And my research group is called Life Enhancing Technology Laboratory. Today, my lecture's title is Human Factors Engineering for Explainable Artificial Intelligence. So I would like to begin with a quick introduction of my specialty area, human factors and ergonomics. Basically, human factors is concerned with the design of tasks, jobs, products, environments, and systems. And in order to be able to optimize the design of these things, we first study the human nature, human limitations, and human abilities. And we utilize such knowledge about ourselves to be able to optimize the design of different systems, like almost everything. So before coming to this seminar or tutorial, I checked what kind of research studies I have been conducting for the last couple of years. And in fact, I mean, there were many different topics, including human vehicle systems like automotive ergonomics, and heavy machinery design like excavator design, mobile devices, blockchain applications, augmented reality systems, foldable displays, and the latest edition is Explainable AI. So as you can see, human factors covers a wide range of application areas. And it's very similar to XAI in computer engineering, but I guess the difference is we not only study computers, but also deal with many other non-computer systems as well. Okay. All right. So what I want to accomplish in my tutorial today is first to provide a quick review of the human factors concept trust. I think that some of you are already very familiar with the concept trust, but nonetheless, for those who do not have much knowledge about this concept trust, this review would be helpful. And secondly, I would like to present our group's recent work on the comparative evaluation of different explanation types for telediagnosis system known as smart chair-based low back pain recognition system. Okay, first, the review of the concept trust in the context of human AI collaboration. Trust is originally from social sciences, and trust has been studied to understand human relationship, but this concept is also very important in understanding human automation or human AI partnerships and collaboration. So according to a widely adopted definition proposed by John Dilly, the reference is up here. So those who are interested in learning more about trust, please refer to this reference. So according to this widely used definition, trust is described as the attitude that an agent will help achieve an individual's goals in a situation characterized by uncertainty and vulnerability. So the attitude refers to the human user's attitude, and agent in this sentence refers to an AI-based system. When it comes down to talking about trust, accomplishing appropriate level of trust is extremely important, because inappropriate trust can lead to undesirable behaviors of the human user, like misuse and disuse and things like that. So supporting appropriate trust is extremely important. So the diagram in this slide shows the concept of appropriate level of trust and what is not appropriate trust in automation. So the vertical axis represents human trust toward an AI agent, and the horizontal axis represent the actual automation capability, the actual capabilities of an AI system. And it's also referred to as trustworthiness. So the line shown here, y is equal to x line, shown here, represents a situation, a desirable situation in which human trust, human attitude toward the ability of an AI system well matches the actual automation or AI capability. So when this situation occurs, when the good matching between human trust and automation capability occurs, we say there is a very good trust calibration. But if human trust is above the actual automation capability shown as this area above the y is equal to x line, so this area, what happens is the human user tends to over-rely on the automation or the AI system. So the human user doesn't really pay attention to the behavior of the AI system and just let it run without really monitoring or checking up on the AI system. And in many cases, such over-reliance behavior can result in like the total system failure and other undesirable consequences. And this area here, the area below y is equal to x line here, is the region of disuse. So in this case, human trust is actually less than the actual automation capability. So when this happens, when the trust is less than the actual automation capability, the human user tends to not use useful AI system. And that's also very undesirable because now the human user has to work more and the human user cannot utilize the useful AI system. So we want to avoid the misuse and disuse of AI systems. And in order to be able to do that, we need to support the good trust calibration, the good matching between the human user's trust and the actual automation capability, which is represented as this line here, y is equal to x. So how do we accomplish good trust calibration? This slide shows a very well-known model of human trust in the context of a human AI collaboration. So human trust toward an AI-based system is affected by a variety of different factors, including individual trait and organizational, cultural, and environmental characteristics like organizational structure, cultural differences, and things like that. So there are many different factors, but the most important factor is the design of information display. So by creating a useful information display that provides information about the AI system or the automation system, like the purpose of the AI system, the process of the AI system, and also the performance of the AI system, it's actually possible to help the human user quickly and accurately accomplish trust calibration. And that's, I think, where explainable AI comes into the picture. And it has a lot of potential to help the human AI collaboration. So in my opinion, I feel that like explanation interface design is a really important consideration for supporting appropriate trust and accomplishing good trust calibration. And I like to share one very successful example of such explanation interface. So this slide shows like one example of an explanation interface, which I found from my readings of like research articles. I mean, the reference is shown here. And this interface is about like controlling a number of military drones. So it shows actually two different interfaces. I mean, the one on the left is like before, and the one on the right is after. Okay, so before and after comparison. So an AI system is assisting a human drone operator in this particular context. And in this figure shown on the left, the diamond-shaped symbol represents a target, okay, on top of a map, as you can see. And there's a number of like drones represented as like bluish symbol, okay. And the AI system assisting the human drone operator basically picks one of the drones for the mission related to the target. So for some reason, the AI system selected this particular, the one highlighted in yellow, selected this one, and then basically the AI system reports the human user that this was going to be, and this is going to be used for some mission, okay? And when given this, the human operator doesn't really easily understand why the AI system picked this particular drone. Although the AI system, the AI system is trying to convey that information using some text window shown here. So it provides some information. But this information doesn't really help the human operator understand why the particular drone is selected among different resources. But the improved interface shown on the right solves this explanation problem brilliantly. So instead of providing information in the form of text, the revised or the improved interface now utilizes the size and opacity of the symbols in order to explain why a particular drone was selected. So in this improved interface, the size of the symbol represents the speed of each drone, and opacity represents the capability of each one of those drones. So the bigger, the faster, and also the less opaque, the better the capability of the drone is. Like better capability means the drone is well equipped. So the semi-transparent drones cannot accomplish the mission, and the solid drones shown here, and here, they are able to accomplish the mission. So by looking at this single picture, the human user or the human operator can instantly understand why this particular drone was selected among available resources. This one is the fastest among the capable drones. So literally, a picture can paint 1,000 words, and that's what explanation interface design can do, especially when it's designed well. Okay, so that's the end of the first item that I wanted to convey today. And the second item, let me move on to the second item of my presentation today, comparative evaluation of explanation interfaces for a smart chair-based low back pain recognition system. Okay, so this material is from our research based on the IITP XAI project, which we joined last year. And initially, our goal was to develop some general UI UX process for like that can be utilized for like almost like every domains, like a very general purpose UX processes, like the design methodology and evaluation methodology and things like that. But a couple of months into the research project, we quickly realized that it's virtually impossible to develop such a general methodology that would be applicable to every application domain. And that's because every domain has like its own like unique characteristics and so on. So in order to be able to conduct research, we decided to narrow down the scope of our research. And we ended up deciding that we'll be working on some XAI type of systems for healthcare, because I mean, healthcare is obviously one of the important application domains. And more importantly, at that time, we already had an AI-based system ready. Like we had some smart chair that we developed in our prior research projects, and this gave us like some something to work with in terms of like getting XAI research done. So this slide shows the smart chair that we've been working on almost like for 5 or 6 years. And basically, this is an office chair and it's equipped with multiple sensors. So 6 infrared distance sensors are embedded in the seat back of this chair. And 6 pressure sensors are embedded in the seat pan of this office chair. So using these 12 sensors, like 6 distance sensors and 6 pressure sensors, in combination with a simple KNN algorithm, this smart chair was able to classify the user's sitting posture as one of the 11 predetermined posture categories shown on the right. So there are a total of 11 posture categories, and so this chair can generate like a time sequence of posture categories, okay, representing the seated person's like posture behaviors over time. And although we used a simple KNN algorithm, the smart chair system for real-time posture classification accomplished very good prediction / classification performance. So the F1 score was above a 0.91, and the darkest bar represents the performance of our smart chair system called like mixed sensor system. And its performance was a lot better than the performance of the previous systems. So it's quite useful. So this particular smart chair was initially just for classifying human sitting postures, but we tried to extend its capabilities for like different applications, including like healthcare applications. So one of the extensions of the smart chair system for real-time posture classification was detection of low back pain, chronic low back pain. So another system that we created is called the smart chair-based low back pain recognition system. And its function is to classify a user as either a chronic low back pain patient or a non-patient. Okay. So by letting a person sit and perform like computer typing task for an hour or so, this new system will be able to tell whether that person is a chronic low back pain patient or a non-patient. That's like what it does. Okay, some facts about low back pain. I'm sure that some of you already experienced a severe or moderate level of low back pain. I mean, sometime in your life. And basically, LBP is one of the most common disorders worldwide. According to statistics, 8 out of 10 people experience severe low back pain at least once in their lifetime. LBP is a significant social problem because it causes enormous economic and social losses. And our low back pain recognition system is for detecting chronic low back pain, shortly CLBP. And CLBP means LBP persisting for more than 3 months. So if you started feeling like low back pain, and if it lasts for 3 months or longer, then basically you're a CLBP patient. That's what it is. Now, let me briefly describe the structure of the smart chair-based LBP recognition system. The posture classification system that I mentioned earlier generates like a time sequence of sitting postures when a user is performing computer typing for 1 hour time period. And a binary classification model, called the CLBP detector, was created, and it classifies the user as either a CLBP patient or a non-patient on the basis of the posture time sequence generated by the real-time posture classification system. And in developing this binary classification model, we use the machine learning algorithm known as the cat boost algorithm, which is a black box type of algorithm. And this classifier, this binary classifier, utilizes a set of features from the posture time sequence generated by a real-time posture classifier. So the features that this binary classifier utilizes are as follows, like relative frequencies of some posture categories among the 11 posture categories that I already described. And also time changes in relative frequencies of posture categories. Like, so we look at the algorithm looks at the first 15 minutes and the last 15 minutes of the 1 hour time period and computes time changes in relative frequencies of some posture categories. And that's also used as part of the feature set. And also number of posture categories observed during the 1 hour time period. So we found that actually chronic low back low back pain patient shows less variability in the posture categories utilized during like 1 hour long computer typing task compared with a non-patient. So that's also a piece of information that can help classify a person as either a patient or a non-patient. So cat boost, the cat boost model, the CLBP detector did a reasonably good job. So the F1 score was like 81.3%. So it's not really great. I mean, but then again, please note that this particular study is the first of its kind. I mean, I don't think, there's any other study that investigated the detection of low back pain using a smart chair-like device. And precision is pretty good, like 95%, but recall is only 76.6%. So there is a room for improvement. But still, 81.3 is not too bad. So I think this is a useful system. Now, XAI questions. So this smart chair-based low back pain recognition system provides diagnosis. And the users, the lay person who utilizes this particular system will have questions when he or she receives a diagnostic output, like you're a patient or you're a non-patient. So here are some research questions related to explanation. RQ1, how can the CLVP recognition system's diagnosis result be best explained to the user? It's a very general question. And right below it, there is a less general question, RQ2, how do existing XAI methods, like typical explanation types described in literature, so how do they compare in terms of XAI evaluation metrics? So the first question, RQ1, is a pretty difficult question to address, and it would take some time for us to be able to find good answers to this question. So instead of trying to address RQ1, last year we tried to focus on the second research question. So we looked at different XAI methods typically mentioned in the literature, and we compared them in terms of their performance or like user acceptance metrics or UX metrics. So I'm going to talk about that. So we decided to conduct an experiment to compare different XAI methods. So in one experiment we conducted, a total of 46 participants participated, and they were all relatively young, like 19 to 33 years old. And half of the participants were assigned to the CLVP patient group, and the other half were assigned to the non-patient group. So those who were assigned to the CLVP patient group will receive a diagnostic output that, like, you are a patient, okay, and also related explanations. And each one of the participants in the non-patient group will receive a diagnosis like you are a non-patient, you are not a patient, and also related information. And the table shows the breakdown of the participant demographic information. So both genders were represented, and the participants actually represented different levels of AI ML knowledge. Okay, so 20 out of 46 participants didn't have much knowledge about artificial intelligence or machine learning, and 18 some knowledge, and 7 of them had a very high level of AI ML knowledge and things like that. And we considered 4 local explanation types. No explanation. This served as the baseline for comparison. And we considered the feature attribution explanation, example-based explanation, decision tree explanation. These are typical methods for XAI. And these 4 different explanation types were evaluated using the metrics shown right below. So 5 user experience metrics like understandability, satisfaction, sufficiency, completeness, usefulness, perceived accuracy, and trustworthiness. Trustworthiness here refers to perceived trustworthiness. So trust, really. These 7 user experience metrics were found in an article by Hoffman et al., published in 2018, Metrics for Explainable AI Challenges and Prospects. And I think that these metrics are very relevant to the evaluation of explanations. And in addition to these UX metrics, we also employed a metric for evaluating the cognitive load of an explanation. So we used the PAS cognitive load rating. There is a typo here. And it's basically a 9-point scale subjective rating system. All right, experimental procedure. So prior to the experimental trials, each participant was informed about the purpose and procedure of the experimental study. And we also had a learning session in which the participants learned about the definition and characteristics of CLBP and how the smart chair-based CLBP recognition system works. And in the learning session, we also taught these participants about the 3 explanation methods considered in this study. So the feature attribution explanation method and decision tree-based explanation and example-based explanation were those 3. And in the actual experimental trials, we created some interface prototypes for the 3 different explanation methods. And so these interface prototypes were presented to each participant. And the participant took enough time to examine and interpret the interface prototypes and then performed subjective ratings for the 7 UX metrics and the cognitive load metric that I mentioned earlier. And the presentation order of the 4 explanation types was randomized for each participant, and counterbalancing was done. Okay, I'm going to show you the explanation interface prototypes. So, the diagnostic output was a CLBP patient. So this is what the participants in the CLBP patient group saw during the experimental trials. So in the no explanation condition, only the diagnostic output was presented to each participant. So you're an LBP patient. Okay, that's what it says. And for feature attribution explanation, first, the diagnostic output was presented, and then the feature attribution explanation was provided, and the interface looked like this. So feature importance values are presented in terms of multiple bar graphs and also in terms of like actual numbers. And for example-based explanation, first the diagnosis, and then the next screen presented the feature values for the case under consideration. I mean the patient. So the patient's feature values, and also the representative examples of the CLBP patient group, and also the representative example of a non-patient. Okay, so the feature values for those representative cases for the 2 different classes are also presented. So this is what a patient or the participant, excuse me, would see in the interface. And for decision tree explanation, the diagnosis is presented, and decision tree, which shows the path of decision making, is presented. Okay, so the entire decision tree and the path of decision making was presented, and also the feature values are also presented in addition. So that's the interface for decision tree explanation. And the interface is presented to the participants in the non-patient group, okay, were similar. So, so no explanation. The participants would only see this screen. And then feature attribution explanation, then example-based explanation, and decision tree explanation. So, okay, so the experimental variables, the independent variables of this experimental study were explanation type, and as I mentioned earlier, no explanation, feature attribution, example-based, and decision tree explanations. And group diagnostic output was another independent variable, and there were 2 levels: CLBP patient and non-patient. And there were a total of 8 dependent variables, 7 user experience measures, and a cognitive load rating measure. And for data analysis, we conducted two-way ANOVAs and also post-hoc pairwise comparisons. Okay, moving on to the results. So this slide presents the analysis of variance results. So what happened is the independent variable group was not significant, was not found to be significant for any of the dependent measures, whereas explanation type was found to be significant for every single one of the dependent measures. Okay. And we found one two-way interaction, like group by explanation type interaction for perceived trustworthiness. Okay. So let's look at the description of explanation type main effects. Okay, so so each one of these multiple bar graphs shows the mean rating values for no explanation, feature attribution, example-based explanation, and decision tree explanation in that order, okay, from left to right. And for understandability, satisfaction, sufficiency, and completeness, the 3 explanation types, feature attribution, example-based explanation, decision tree, showed like better results than no explanation. Okay, so providing some explanations using typical explanation methods were found to be actually useful. It improved like user responses compared with like providing no explanation. And also another thing that we can observe from these results is that the decision tree explanation was found to be better than the other 2 explanation methods, like, I mean, feature attribution explanation and example-based explanation. So for understandability, decision tree explanation was significantly better than feature attribution and example-based explanation. And although although not statistically significant, for satisfaction, sufficiency, and completeness, decision tree seemed to be better, okay, somewhat better, but there is no statistically significant difference. For the other 3 UX metrics, usefulness, accuracy, and trustworthiness, what we found was the typical explanation methods resulted in better user responses compared with no explanation. But among the 3 explanation methods we considered, I mean, there's not much like significant differences between them. This slide shows the results for the cognitive load rating. Okay, so the higher, the more mentally demanding. Okay, and it's based on a 9-point scale. So no explanation resulted in the least amount of cognitive load, and that's not surprising because, I mean, if there is no explanation, there's no information to really process, right? So that's why no explanation was associated with the smallest cognitive load. And for the other 3 explanation methods, what we found was like the decision tree explanation was the best, okay, compared with the other 2. And it resulted in the smallest cognitive load among the 3, okay. And this slide shows the 2-way explanation type by group diagnostic of interaction effect. So positive means CLVP patient. The diagnosis is CLVP patient, and negative refers to diagnostic output being no patient. Okay, so what it shows is that the utility of a particular explanation method can change according to context. So, for example, for decision trees, trustworthiness, perceived trustworthiness was better when the diagnostic output was non-patient compared with when the diagnostic output being a CLBP patient. So it's interesting to see that on explanation methods, utility in general can change, like as context changes. But then again, the magnitude of the effect that we see from this particular analysis is not really great. It's not really large. All right, discussion. So what we found is that compared with no explanation, the 3 explanation types mentioned in the literature and used a lot resulted in better user responses. So this indicates that the existing XAI methods are useful. It's better than nothing. And overall, decision tree explanation appeared more advantageous compared with the other alternatives. And the other alternatives were feature-based explanation and also example-based explanation. I already mentioned that the decision tree explanation was better than the other alternatives in terms of understandability and also in terms of cognitive load score. Now, so why is decision tree explanation better than the other explanation methods? Our interpretation is as follows, I mean, shown on the slide. So the reason, we think that the reason decision tree explanation did better is because people are already familiar with the use of if-then type of rules in describing a decision process. In addition to that, a set of if-then rules fully and directly describes how a decision is made. So it's very straightforward. If you just follow the trajectory or path of decision making described in a decision tree, then you will understand exactly how the AI system made a particular decision. But on the other hand, the feature attribution and example cases do not really describe, fully and directly describe the decision process. They are indirect in describing a decision process. And also another reason that we thought of was that understanding the notions like feature importance and example cases requires some mental models associated with AI ML method. So in order to fully understand the meaning of feature importance and example cases and so on, you have to have a certain amount of knowledge about AI ML. Without such knowledge, I mean, it's not really possible to understand the meaning of the report presented by the AI. And remember that 20 out of the 46 participants who participated in our study didn't have much knowledge about AI ML. And although we provided some learning sessions, I mean, I really doubt that, I mean, they actually fully understood like what these explanation methods are and how they work and things like that. And another thing, excuse me, okay, when using decision tree explanation, the user only needs to process a single if-then rule at a time, one at a time, basically. So a decision process can be broken down into a series of simple operations, okay? Simple comparison type of operations. So it's easy to process. Decision tree is easy to process, but on the other hand, feature attribution explanation requires integrating multiple feature importance and values and needed to, like, the user need to understand the overall meaning. Okay? and that's like more difficult. And example-based explanation also requires comparing the case of interest with each of the examples, the representative examples presented in the multi-item vector representation. So such mental integration is mentally very demanding, and therefore it could compromise understandability. And in addition to compromising understandability, the requirement that the user has to integrate like many pieces of information, like a large number of numbers, right, will also compromise or increase the mental workload during the processing of the information. And so decision tree doesn't have that. So decision tree, that's why decision tree explanation resulted in significantly lower mean cognitive load score. But the other two explanation methods like feature attribution and example-based explanation, because I mean they require mental integration of many pieces of information, cognitive load rating was higher for them. So that's our interpretation. And once again, the two-way interaction effect that we found, the explanation type by group interaction effect is quite interesting because it suggests that the utility of a particular explanation type would change according to a machine decision and its implications. And we think this warrants further investigations. And lastly, why is the explanation types considered were found to be useful compared with providing no explanation? We have to admit that I have to admit that their mean ratings were not so great. So on a 5-point scale, the mean values for the UX measures were less than 4. And the cognitive load scores were greater than 4 on the 9-point scale. So they are not really great. And there is room for improvement in terms of improving explainability. So what we think is that the explanations based on the existing XAI methods may not address the real information needs of the users in the particular context of a smart chair-based CLVP recognition system. Although these explanation methods, like mentioned in the literature, are useful, and we saw that, but they may not really hit the bullseye. I mean, they don't necessarily represent the real information needs of the participant. And we also think that predetermining user information needs based on some existing framework or existing XAI methods may not be desirable, and it may not be really possible to anticipate user information needs in advance. So a better approach might be discover user explanation needs specific to each particular AI application context through contextual inquiry and analysis. But the problem is, I mean, there is no well-established method for such contextual inquiry and analysis, and that's, I think, a future research topic. So conclusions. Overall, the existing XAI methods were found to be useful, but there is a room for improvement. And decision tree-based explanation seems to have some good properties. And new methods for contextual inquiry and analysis are needed for improving XAI interface design. And I guess, I mean, that's the end of my presentation material, and I hope I didn't exceed the time provided for me. Okay, that's it. And I'm going to entertain some questions.